Hi guys. So today I'm going to present my show and tell on China salesman algorithm problem or the Postman problem. So basically this problem was by a Chinese mathematician Quan Mei Ko in the early 1960s, 1962. So the problem is that this Chinese postman wishes to travel along the road in a city in order to deliver his letters with the least possible distance. And we have to find the shortest close walk of the graph in which edges is traversed at least once. So this problem differs from the regular traversing salesman problem whereby each edges is only allowed to be traversed once, but then the Chinese postman problem allow you to travel more than once. So the algorithm that I found online of how to solve this issue is by graph theory. So how this graph theory actually works is that firstly, all the nodes are actually labeled, and then you have to define the odd nodes within the graph. So how you define an odd node is the amount of edges that actually that it can traverse on. So you can see that for A wise, there's two routes, which is AD and AB. So this is considered an even node. So odd node would be something like odd node B, which is like AB, BD, and BC. So there's three ways to reach to the B node, so it's considered an odd node. So the first point of the problem is, the first part of solving it is to first get all the odd nodes. So all the odd nodes in this diagram would be B, C, D, and E. Then the next step is to actually pair them up. So considering the four nodes available, the pair options are BCDE, BDCE, and BECD. Then based on these pairs, you get the shortest way to get to each node. So from BC wise, you can see the shortest way to get is 3, and for DE, which is obvious, is 4. But if you take a look at BD and CE, you can see that the direct option from B to D is 5. But then there's a shorter way of traversing, which is from B to A, and then from A to D, which would be a 3. And there is also a longer way, which is B to C, C to F, or C to E, then E to D. So getting all these ways of traversing, we get the shortest way available, and then I put an asterisk on all those that does not take a direct route to the next node that they were supposed to go to. Then from all these pairs, we choose the shortest option available, which in this case would be BD to CE, which would be a 3-3. So how do you actually count the number of steps required to actually reach to the final goal is to take this smallest pair and sum up the total amount of traversing required throughout the whole graph, and you should get the number 30, which is 24 of the entire graph plus the 3, which is 6. And then brings us the question to then how do you actually traverse the entire graph? So if you take a look at this short animation I created, is that we consider the starting point A, you move to B, B to C, C to E, and then you traverse back based on the BD and CE point, which is from CE you will get to F, then you go back to C again, and then you come down to E, you go to F, and then you come down to E again, you go to C, up to B, go to A, down to D, and then back to A again. So this is the path that I've sort of write out. But this is not the only path. You can find other ways to traverse. As long as it follows this same algorithm, it will be the shortest path available. Then also online, I found an additional question to this similar problem is that what if you can find a different place as compared to the starting point, then where should you start and where should you finish? So based on this problem, right, it's the same algorithm. You get all the nodes and then the odd nodes, and then you pair them up and then you add up the sum. But now instead of getting them in twos, you get the smallest one available. And then since we already use BD and CE, let's use BC for this case as the point whereby it's allowed to traverse more than once. And the total traversing required will be 27, and then the road will be whichever way that you go, but then BC will allow you to walk twice
So you can traverse from any point. But then the start point will be directly opposite of BC, which will be either D or E. So some practical application of this algorithm in real life is routing of bus services around the world. So this helps bus companies to actually save cost on fuel consumption, and then bus companies model the bus stops as the vertexes and the roads as the edges along the bus route. And then graph theory obtain the optimal route that can meet the target of using minimal fuel but cross every road and bus stops at least once. Other examples include trash collection, road sweeping, transmission line inspections, school bus routings, etc., etc. And with that, I've come to the end. Thank you.
Any questions? So why is it called the Chinese Postman problem?
Okay. It's the Chinese postman problem simply because it was found by the Chinese mathematician. So because she founded it, so they named it the Chinese postman problem. And then she had this idea based on the initial traversing salesman problem, and then she came to think of how this problem could be even more complicated in real life situation. So she came up with the postman problem in a village situation.
All right.
Thank you.